Okay, section 7.2 brings us to velocity and applications of velocity with vectors. To warm up, we're going to do just a straight conversion. We've really got to watch when we problem solve for units and make sure that units correspond with each other in any of the formulas that we have to use. So common application is a conversion between meters per second and kilometers per hour. Now you can set up a wide variety of ways to convert units and velocity units in particular. You can multiply by the ratio. I think in this case it's 3.6. That's on the first. That's on the online version. So for 1 meter per second is equivalent to 3.6 kilometers per hour. Or you can set up a ratio. You can go online to find a converter, easy converter to do online if you want to avoid the work. And you can also understand, I'm just going to do this real quickly, understand exactly how this works. So in this particular conversion, we want to start at 5 kilometers. Okay, so 5 meters per second, and we can start multiplying by some common ratios. So remember, our end goal is to have kilometers in the top and hours in the bottom. Okay, so the first ratio I would go is to change from meters to kilometers, and I know my common ratio, or you might know that 1 kilometer is equivalent to 1,000 meters. Okay, now when I write it like this, my kilometer unit is going to stay in the numerator, and my meters is going to actually cancel out. Okay, when I actually do the multiplying. Okay, and we can cancel units like we can cancel factors, right? Okay, so the next thing now is I want to multiply by. Let's do the time conversion. I know, and I might know just through my background knowledge here, that 60 seconds exist in 1 minute. Okay, that's a pretty, I think, a common sort of understanding here. And I also know that 60 minutes occur in 1 hour. Now, when I've done it this way, and this is a little bit of intuitive, okay, I want to then start canceling units, just like I did with the meters and kilometers here. So notice that, okay, I want hours in my denominator, and I have hours in my denominator. My minutes will cancel, and this second will cancel with this second here. So what I'm left with when I cancel units, okay, my kilometers per hour here, and that's kilometers per hour. So now I just multiply my numbers together. 5 times 1, okay, times 60, divided by 1,000. And 5 times 1 by 60 divided by 1,000. Okay, I'm just going to get my calculator. Okay, 5 times 1 times 60 divided by 1,000 is approximately 18, and it's kilometers per hour here. Now I think that factor, if I'm going to go back to my lesson, and right here in the unit, right here in the beginning of the 7.2 lesson, okay, is this common ratio here. And I could have did 5 times 3.6 and got 18 kilometers per hour. So if you like, okay, you could do it that way. Okay, or you can understand as I did here, sort of help explain and understand that there's a reason why that ratio works. Okay, so I could have did, if I remember that ratio. Okay, here's the reason why it works. Okay, and that helps too as well. Okay, the next question involves a boating situation. So a river flows eastward at 4 meters per second, and boat heads down the river, downstream. Okay, so downstream and upstream is a bit of a new concept here. We'll discuss this in a second. But, the rest of the question goes: the motorboat is traveling between two towns which are 50 kilometers apart, and if the motorboat speed in still water is 12 meters per second. So this is without the current here. Okay, so let's do a couple of things before we get started with this. First of all, I'm going to convert the 50 kilometers to meters to match our speeds. Okay, so that's multiplied by a factor of 1,000, because there are 1,000 meters in 1 kilometer here. So we've got, sorry, that's 1,000. 1, 2, 3. Okay, and that's meters. All right, so downstream and upstream. So downstream is when I go with the current. Okay, so I'm using the current to help me along here. So the boat, okay, is heading downstream. Okay, the velocity vector of the boat, okay, is going to be, okay, the velocity, okay, of the boat, okay, the boat in still water, I'm going to call that, and the velocity of the current. And we've got 12 meters per second and 4 meters per second. So when I use if I'm driving this boat and I use the current to help me, and I go downstream, I can go at a speed, okay, of 16 meters per second. Now, the time required to cover the distance between the towns, time, okay, is found using the velocity time, and time, okay, is distance divided by velocity. And in this case, okay, so it would take me, okay, 50,000 meters, and I can go 16 meters per second. I can get there in 3,125 seconds, and if I convert that to minutes, okay, that's approximately 52 minutes to get to that area here. Okay, this factor here is, and I know velocity is equal to distance over time. I can set up, and we've seen this in the previous, it's a pretty bad triangle here. Let me try that again. What did I say? It was, okay, velocity equals distance over time, and I use this triangle here. You've seen this in science probably. Okay, where time is distance divided by velocity, and that's what I used. Okay, upstream, okay, is going opposite the current. So when I'm heading up the river, I'm going against the current. So this particular velocity, okay, is going to be, okay, when I subtract this amount, so that's going to be 12, okay, take away 4 in this case. So I'm going against the current. So I'm going, my boat's, okay, going at a speed of 8 meters per second. I've got to cover the same distance traveled, so the time in this case is going to be that same 50,000 meters, but I'm going at a different speed. Clearly it's going to take me a little bit longer. Okay, I get a calculation, okay, and that's approximately, okay, 1 hour and 44 minutes. And I just take that, I just divide 60, okay, 60 by, okay, or sorry, that elapsed time by 60 to get 52 here. That's exactly how I do that. Okay, so that's basically how I understand that, and we want to make sure we understand, okay, downstream, okay, is with current, and upstream, okay, is against the current. All right, let's get on to the next one. Okay, this time it's a plane and wind speed velocity question. It's a plane scheduled to travel from airport A. I've got it all on my diagram to airport B. The distance, we'll deal with the distance down in part C of this to calculate how long the trip will take. I'm not going to be too concerned. I want to make sure I keep my vector quantities straight, and that's going to be the plane speed and the wind speed, separate from my scalar quantities, and that's a distance. Okay, so I'm going to focus on that a little bit of time here. So first thing I have to do is consider the vector system that gets created when I've got a plane traveling at 300 kilometers per hour. That's my vector over here, the plane with respect to the air, is 300 kilometers per hour. That's this vector here, represented in red. And at the end of that vector system, I've got the wind speed that's across the top. I think that's in purple or maybe blue. The vector speed of air with respect to ground, and that's 100 kilometers per hour. So what direction should the plane head out? And I'm going to try and find that to be beta, that angle beta here. So for A, I'm going to do a sine law just on this small vector system here. So that'll be the sine, okay, of beta, okay, over, okay, 100. That's my corresponding vector across that side, and that's going to equal, okay, the sine of 30. I've got the other ratio here across from 300. Okay, so when I cross multiply, and do a little bit of calculator work and then do inverse sine, I get beta to be, okay, approximately, I'm going to round off here, approximately 10 degrees. I think it was about 9.6 degrees. I'm going to round it to 10. Okay, that allows me, okay, to, okay, calculate the other angle. Okay, okay, lambda maybe, I'm sorry, I should know these. That's going to be 90 minus the 10 I just calculated, minus the given angle of 30 degrees here, and that works out to be 50 degrees. Okay, and that's going to be my, okay, my bearing of the plane. Which way should the plane head out? Okay, so it should be, okay, as an orientation, okay, that's east of north, okay, or north, I could say north 50 degrees east. Okay, so the plane should head out, and let me change my pen color. So the plane should head out at this direction. It's going to get knocked off course, okay, by the wind, but that'll allow it to, okay, head up to, okay, head up to the airport. Okay, what speed should the plane what's the speed of the plane relative to the ground? Okay, and that's, okay, that's a calculation that I'm going to use the cosine law here with this one. Okay, so that's trying to find vector in green. Let me change my color to do that in green. Okay, just to match, that's the vector PG. I'm going to, okay, square that, and I'm going to set up the sine law, or the cosine law. So I've got my closed system, the vector system is 300 plus 100 minus 2 times 300 times 100, and then the cos of, I've got this angle right here, and I think this angle right here is 30 and 10 is 40, take away 1 from 180, I've got 140. Okay, I should be able to find all of this calculation. Okay, don't know what it is, but then I've got to take, sorry, the square root of whatever that is, that whole expression here. I didn't calculate this in my notes on my calculator step by step, I think, but I think at this stage you guys should be able to do that quite easily. I do have a final answer here of 382, okay, 0.05 kilometers per hour. And again, that's makes to be like a sensible answer. It looks like it's going to be greater than, see, remember, the plane with respect to the air is going 300. It gets knocked off course by 100 kilometer per hour wind, and that's obviously going to speed up the plane from its original 300. So that seems like a sensible answer here. Okay, finally, C. How long will the plane take? How long will the trip be? And C is a time question. We learned earlier that I can use, okay, a time calculation, and I've got 600 divided by 382.05. I get a time to be about approximately 1.57 hours. Okay, now we should, okay, that's about 1 hour equivalent to, and then I take the decimal and multiply by 60. I get about 34 minutes approximately. So in practical terms, it's a 1 hour and 34-minute trip. So I should sort of talk about that and write that. Okay, on to the next one. All right, next up is another river and boating problem. 800-meter wide river flows eastward at 10 meters per second. Peter's driving his motorboat heading perpendicular to the current. So Peter's represented in red. That's the boat with respect to the water vector. The current vector is represented in purple or dark blue here. That's the vector of water with respect to the ground. That's going at 10 meters per second. And I want to find the vector green, the boat with respect to the ground. The speed of the motorboat is the boat with respect to the water. That's in red. That's 20 meters per second. And I want to find A, that's the green vector. Here, I want to find the vector, the speed of the boat with respect to the ground. And that's this green vector. So I'm going to focus on, just like the last question, I'm going to focus on this small triangle right in here, this system. Okay, so this is for A, this small system of vectors where I have 20 and 10, and I want to find V at B, G if I like. Now it happens to be a right triangle, so I don't need the full cosine law. If you wanted to use the cosine law, you could, absolutely you could. It would be the angle, okay, the angle across from this resultant vector is 0, and the cosine of 0 is 0, or sorry, the angle across from this corresponding vector is 90, okay, and the cosine of 90 is 0, so really that whole extra piece gets sort of negated here. Either way, this question, okay, uses the cosine law or simply just the Pythagorean theorem. Okay, so I have this simple little system to solve, and it works out to be approximately, I think, 10 root 5, or rational to 22.36 meters per second. Okay, so that's how fast Peter's is moving. The boat's moving along here because he's got his speed of the boat plus the current here. So how long does it take to cross the river? Okay, so that's B. I've got a river is 800 across. I'm going to use similar triangles for this one. Okay, I've got this across the river, and I've got this small vector here. Now our small vector was 20 and 10. Okay, and I found this one to be 22.36. My large triangle is 800. Okay, and I want to find basically this corresponding distance here. So I could do it in a couple of ways. Okay, I certainly could find this corresponding distance and use the Pythagorean theorem. Okay, or I could get that distance here. How long does it take to cross the river? Either way, I'm going to need this distance right here. Okay, the full distance of his path. Now I think I'm going to find this distance across here from points A to B. Okay, so if there was no current where Peter would land his boat, but if this is the practical, this is where he ends up going. Through common ratios, I could go 20 over 10. 20 over 10 is equal to 800 over x. That's my corresponding solution. I get x to be 400. Okay, that's the answer to C. Okay, incidentally, but now if I had this to be 400, this to be 800, I could use the Pythagorean theorem to find the distance D. That would be 400 squared and 800 squared. I get B to be, if I did this properly, 894. 0.43. So the time it takes to cross the river, okay, when I travel a distance and I go with a certain velocity, my velocity was from A, 22.36, I get approximately 40 seconds. I think it's exactly, and I think you guys probably see how this kind of relates to similar triangles here. Okay, certainly I could have set up any type of ratio. I even could have used the ratio for the velocity side and did all kinds of work there. C I already found, okay, to be 400 meters. Okay, a wide variety of ways to do that. Keep, as I said though, from the previous example and in this one, keep it simple with respect to the vector system. First of all, question A, okay, focuses on just looking at the vector system here and how that works out. Okay, next one again is another swimming water current question, similar to the boat question. I'm going to just introduce this, pause it, and let you guys do this based on our last example and see where you're at with this. Then when I return to the video, the solutions will be there and I'll walk you through a little bit of that. Okay, so first of all, we have a diagram. That's good. Jane can swim 5 meters per second in still water. She wishes to swim across the river 200 meters directly opposite where she's standing, okay? But she has to deal with the flow, westward flow of the current at 4 meters per second. Westward, okay, a couple of things before we get started here. Westward, I think that means that it's going towards the west, so it's going from east to west. Now, before you get started, I want to strongly encourage you guys to solve problems this way and realize that, you know what, if I don't know exactly how to solve it, I have to make an assumption or make a guess and then proceed with my solution. So if you're ever stuck with maybe trying to understand how the question is written or how you interpret it, don't just stop doing it. Okay, make a good informed decision and go forward with it. And good teachers will mark it accordingly. So I think we've got this situation here, and I want to find. Okay, so she's standing on the south bank. That's Jane right there at point A, and she wants to swim across at B. We know what she can swim in still water, and we know she's getting pushed off course, and we're given this distance. We'll deal with the distance at the end, but we'll get started with some of the other aspects of it. Okay, try it on your own, and we'll get back to you in a minute. Okay, our last question in this section is the Jane swimming in the water and crossing a small river. So I use colors to match the diagram. We talked about the intro to this. So the first question is Jane's speed relative to the ground. It's actually given in the question. I'm not sure why it's asked. Maybe a bit of a trick question. That's the vector represented in green. That's the vector with subscripts J and G. So that's Jane with respect to the ground, or if I'm standing on ground and I watch Jane swim across the water, that's how fast I notice that she's going here. That's 5 meters per second going in the north direction. B, okay, is the angle on the diagram. I used the black marker for that. That's just a simple little triangle here. We can use the tan ratio for that. That's so the tan of theta is equal to 4/5. Inverse tan of 0.8 gives me 38.7 degrees for theta. So that's how if she doesn't account for that, that's how much she's going to be knocked off course for that. So you can either look at it two ways here, and that's kind of why the westward or eastward current doesn't really matter too much. Okay, so let me explain that for a second. If that was the angle that she swam at, so if she set off from point A and swam along the red vector, at that angle 38.7 off orientation sort of thing, the current would push her back. So if the current was flowing from the west to the east, it would push her back so that she would hit B as she moved across here. If it was interpreted the other way, Jane would actually have to swim this way, okay, at a similar triangle, right? And that same angle would be the case here. and she'd swim that way and she'd get pushed that back way and she'd end up at B. So either way, that angle is found just like that. Okay, so it's all about just reference points and how you interpret that question. C is a little bit harder. How long does it take for her to cross the river? So we need a time. How long does it take? I need a red vector, that velocity of Jane swimming in the water. That's the speed of square root of 41. So that was just 4 squared plus 5 squared. Work that out. Then I set up similar triangles here, set up ratios, found on my large triangle, that's the whole river, right? I found the distance that she swims, 256.12, and then the distance that she's off course here, and that's a distance that's represented by x, so that would be 160. Either way, the time that's going to take her, okay, it's the distance that she's got to cover in the water divided by her speed, and that's 256.12 divided by square root of 41. I never did work that out. Either way, I got time to be 40 seconds. So that finishes vector section 7.2 with vectors as velocities, and the homework solutions are posted. You guys can work through those. Don't stress too much if you can't get one or two. Just keep trying and check my solutions as you work through this. Okay, good luck.